Okay, so let's finish up here with our final keynote. We are delighted to have with us at this inaugural Robotics Summit event, Marc Raibert, speaking on mobile manipulation robots. Marc is, of course, the well-known CEO of the well-known Boston Dynamic, the maker of those very videogenic and jaw-dropping YouTube videos that come across our computers, a couple times a year. I've known Marc for a while. He is an MIT guy, and then he was out at Carnegie Mellon University, where he started up the Leg Lab out there, and then brought that back here to the Boston area and ran the Leg Lab there for a while, formed Boston Dynamics, and have been creating these very wonderful pieces of technology, these legged bipedal robots and quadrupedal robots. And so without further ado, I'd like to introduce him up on stage to give a presentation that's designed specifically for this audience. So with that, let's welcome up Marc Raibert.
Thank you, Dan. Am I live? Here, I'll do a demo to start with. Look at that. That is really incredible. It really is incredible. I used my eyes. I used my hand. I'm keeping it stabilized while my body moves. Okay, I'm going to do another one. Oops, there's a block in the way. I'll go around. Okay, I'll do another one. Oh, there's a block in the way. I'll step up onto it and then over it. It's amazing. That's pretty much what we want to do, or at least get our machines to do. Hey, it's great being here. I feel like I'm in a room full of friends, fellow roboticists and other enthusiasts. Thanks for having me here. Thanks, Dan, and others. So I'm going to give you a progress report on the work we've been doing at Boston Dynamics, building legged robots. And I guess I have three messages. One is there's still a lot to do, and we're working on some of those long-range things. Another one is I think that some of our work is ready for products, and we have a robot product in production that'll be ready next year. And the third message is we're hiring, and I hope that half of you quit your jobs and come apply and work for us. So I think our grand goal at Boston Dynamics is to make robots that have the level of functionality and performance of people and animals. That doesn't mean that they have to look like a person or an animal, or that they even have to work the same way, but they need the mobility, the dexterity, the ability to use our hands, the perception, the ability to use our eyes and all kinds of other sensors, and then enough intelligence to pull all those pieces together to make robots that can work in the real world doing useful tasks. That's a tall set of goals. I don't know. And in some dimensions, I think we'll get there soon. And in some dimensions, it'll take a long time to get there. But that's the grand mission. But we've organized our company around doing two things at once. One is to work on the long-term goals, really solving some of the big problems in robotics. And I would say that that's what Boston Dynamics' mission has been since we've been working on robotics for the last 15 years or so. But the other goal, the new one for us, is to convert some of the technology, which has been advancing, into useful products that we can sell and eventually make money with in the much shorter run. I think it's a little bit of a challenge to do both of those things at once, but we're committed to trying, and that's where we are now. So I'm going to talk about what we're doing in each of those areas. In this chart, the blue area we think of as the shorter term achievable kinds of applications, because the level of manipulation and the level of mobility are, I'll call them modest. And then the yellow area represents the things we'd really like to do, but it's going to take longer to reach. And so what's on here? Entertainment. I think making robots that are entertaining and that are like entities moving in the world is really achievable, and we're going to see more and more of that very, very quickly. I think security, meaning having robots that patrol a site and provide information about what's going on at the site, maybe video recording or video links, or possibly interventions in some cases, is imminently doable in the very short run. Parcel delivery is a little bit at the edge of the circle. I'll show a video with a little bit of testing that we've done on the idea of being able to deliver parcels with a legged robot that can go up your stairway and through your door. But I think that there's a lot of desire for that. I'm not sure all the pieces are in place yet. And emergency response is an obvious thing. I've traveled to Fukushima and looked at some of the situations there, and they still have people in suits cleaning things, and you'd really like to have robots in those spaces doing it, possibly with a remote person or possibly some of it autonomously. I think the next frontier is going to be, maybe I won't go through all of these. The ultimate is taking care of disabled or elderly people. There's a lot of people in the United States. It's a number like 31 million people spend about half of their working time taking care of a loved one or a disabled person. And that can be a real burden. I know it's a good thing to be doing, but if we could find a way to help them do that, that would be a real home run. It's going to take us many years to get there. I'm not saying that we have a solution there, but I think that's sort of one of the holy grails. And of course, having a servant in your house would be, a robot servant in your house would be nice too. This is sort of a rough statement as where I think we are with our existing robots. I'm going to go and talk about some of these in terms of the level of capability along that same kind of chart. I've only shown mobility and manipulation on this chart. Obviously, there's many other degrees of freedom that really matter. Cost is a big one. Reliability is a big one. Intelligence probably should be on the list somewhere. And all of those things factor in with trying to make robots into useful tools. This is just sort of a recap of background that shows some of the projects we've worked on over the years, and then I'll talk about the ones we're working on more recently. We specialize on dynamic robots that are actively sensing and balancing themselves as they move, and this is Big Dog from close to 15 years ago now, where it's got gyros and computers on board that let it adjust for activities in the terrain. This is LS3, which we tested all around the United States, sponsored by DARPA. Much of the work in this phase was sponsored by DARPA. It could bushwhack. It was following a human leader, so there's no one driving it with a joystick. It's semi-autonomous. And here it's operating in deep snow, about 8 to 10 inches, which is really hard for wheeled vehicles to do. And it's the real calling for legs. This is the Spot robot, which we built in the last 4 or 5 years, which took the lessons from Big Dog and Cheetah and LS3 and rolled them into a machine that's a little bit smaller and much more agile. And in a couple of minutes, I'll get to where some of the agility of this robot comes from. But here we are testing the idea of doing home deliveries in the Boston area, and we sent the robot to about 20 of our employees' homes, and of course we told them we were going to do this, and their significant others were all on board in order to test that. And we did very well, somewhere in the 70 to 80% success rate. And here we've put an arm on the robot to do mobile manipulation. And this demo right here, where we're interfering with the robot doing its task, I think is the most important thing I have to show. Because it says that the robustness in performing, and this is another example of the same idea, the robustness of the robot in performing its task is much more important than being able to perform the nominal task, which is the undisturbed, open loop type activity. You really need to have this level of replanning or sensing and reacting in order to make robots that are smart enough at the low level so that you can use AI and planning and higher level of intelligence to tell them what to do. I don't believe that high level intelligence can know so many details about the world the robot's working in or at least it's a cumbersome model, and I think having as much local intelligence in the machine as possible and resistance to disturbance is the way to go. And we work on that in everything we do. So these are the 4 robots that we're currently working on. I'm not going to say really anything about Spot. It's slightly less active than the others. But I'm going to talk about SpotMini, which is a robot that we're turning into a product that will be available next year, even though we're doing testing with some early customers this year. Atlas, which is a much more futuristic robot, more expensive, more complicated, but it lets us get at topics and problems that are sort of the dreams of what a robot could be. And then I'll just say a word or two about Handle. So SpotMini is a robot that weighs about 60 pounds. It was scaled with the idea of making it small enough to fit in a house or an office or a warehouse where things are really constrained. When we developed Big Dog, which is bigger, we thought that having it roam around in the woods was the toughest mobility challenge that there was. You know, the terrain is totally organic and unstructured. But it turns out that if you take a robot inside of a home, it's a much tougher problem. Everything is really tight and cramped, at least depending upon the scale of your robot. You can't leave black marks on the floor or the walls or on the treads of the stairs. So you can't really go bouncing around in the place. And there's a lot more geometry to the space that's involved in negotiating. So we've been focusing on that challenge, not so much homes, but offices. And SpotMini is designed to be the right size to do that and to be able to have capabilities for doing that. So part of that is to solve what we call the Persian rug problem. You know, our previous robots are hydraulic. And hydraulics is fantastic. Atlas is still hydraulic. I really believe in that. But if you just drop one drop of greasy oil on the Persian rug, you know, you're in trouble. And so we made SpotMini all electric. We put cameras on all sides so it can maneuver in those type spaces. And we've also designed it as a platform, which I'll get to in a minute. So this video just shows SpotMini. I think some of you, obviously we have some of this out on the web, so you've seen this before, but I think there's a few shots in here that are new. Here it has a manipulator on it, but that detaches, so that's sort of an option. And this isn't a real house, and those aren't real people, those people are engineers. This is a mock-up of a house where we do testing, and you can see we have lots of black marks. And this is I think this is the Schraff building where we went to do testing. We go on field trips to test the robot in lots of different environments in order to figure out what the limitations are of the current level of implementation of the software. And here the robot is planting its footsteps, treating these like stepping stones. Imagine there are alligators between the stepping stones, so it doesn't want to step there. And this is just a very tight space where it has to reason about how to move. Both its footsteps and its body and even its knees can get in the way. And here's a dynamic obstacle that it can work around while it's walking. And here, pulling all those pieces together, the ability to plan footsteps, to have balance and reflexes, you can have the robot operate in a very rough, unstructured terrain. That's an ordinary chicken. But it's amazing what the chicken can do in stabilizing the end effector. You know, in a chicken, it's the beak. And in our robot, it's the hand. And it's really important if you're doing mobile manipulation to be able to keep the hand still and under control, even though it's on a mobile base. So I said this before, you know, I can move my base around and keep my hand. Here, I'll touch the corner of this podium without exerting any large forces. And that means that there's a lot of coordination and sensing going on. And here, we've pulled those elements together. We had to bring the foot into action because the door is so heavy little old SpotMini couldn't quite hold the door open without propping it that way. And here, once again, we're giving the robot a hard time, not because we're mean, not because we're angry. The robot's not upset. It's only to show that the robot can keep performing its task and work around disturbances in order to get the job done. And I think that's, again, that's a really important capability that we work on all the time. It's not all where it needs to be. So the organizers of this conference in their press release said that I was going to show you what's under the hood. So I usually don't do that, but I thought I'd put in a few slides about what's under SpotMini's hood. So one thing is the constrained mobility planning system that lets the robot manipulate in very tight spaces or when there's obstacles. So in this picture, the big dark red circle is an obstacle where the body can't go. So that could be a wall, it could be one of these tables or a chair, but it's some big thing where the body can't go. And the other kinds of obstacles are foot obstacles. You saw me avoid this box there. That could be considered a foot obstacle. And also the feet really don't want to go too close to the big body obstacles. That's why I can't point here, but that's why there's pink around the big red circle there. And so we have a system that takes geometric information like this that's acquired by the vision system, and then it creates a nominal body path. It creates a footstep plan. It does all this with quadratic programming, and it uses a limited horizon type model. So every tick, which is about 1/10 of a second, it plans out between 1.5 seconds and 2 seconds into the future and solves for body obstacles, foot obstacles. It has to keep itself balanced even when it moves the feet around. And that's what this process does. And we run it at a very high rate. We have a very clever implementation. We think it's a clever implementation, a high-performance implementation of the QP solver that's running to do this. So here's an example of how the system figures out that it has to keep the body away from that obstacle where those hash marks are. It's readjusted all the footsteps to avoid the foot obstacles, keep it away from the wall, and it's spread them out so that it has a reasonable chance of keeping itself balanced as it goes on the gate. And again, it plans this thing out about every 1/10 of a second, and then executes just till the next 1/10 of a second and plans out again. So this thing adjusts as the environment changes. You saw us roll that ball in front of it when it was moving. It was accommodating that by replanning with this limited horizon that. Another element of our control that's under the hood is the approach to controlling the dynamics of the robot that we call sequential composition. And Al Rizzi and the crew who works for him have been the original. Al Rizzi is at our place, the head of the SPOT program. They kind of invented this approach some time ago, and we've been cultivating it and developing it and making it practical for these robots. The basic idea is to take the complex dynamic space of a multi-legged robot that's interacting with its environment and break it down into regions where the control isn't so complicated, having some formality about what happens when you cross the boundaries of regions. That's really where the magic is. And we don't actually have magic. We have workable solutions to how you do those transitions. And then one of the most important things about it is once you've divided up the space, it allows programmers or developers to work independently on separate aspects of the problem. So as an enabler for our development crew, it really is a big deal because we have lots of people working on aspects of a problem where they're coordinated in how their parts interact, but can work separately to develop more quickly. I think this approach might even be more important, I didn't write it on the slide this way, more important than machine learning for getting complex moving robots to make progress. although part of that is making a system or a structure where machine learning can be brought to bear and solve some of the boundary problems, better define the boundaries and better define some of the behavior within these boundaries. But this structure really lets you open up the problem and facilitates an approach like that. So that's all I was going to show under the hood. I said SpotMini is in the process of becoming a product. We've reduced the cost of it. I'm not going to tell you what it's going to cost yet, but it's about 10 times less expensive than the early prototypes of it, so we've been working hard on that. We're working with contract manufacturers. We built 10 by hand. We're building 10 by hand, but of something very close to the production unit. We're doing 100 at the end of this year, working with contract manufacturers, and we hope next year, about the middle of next year, to be in a rate of production that's about 1,000 per year. We've designed the system as a platform, both mechanically and computationally. So there's a place to mount things. You can mount an arm on it. We make an arm, but you can put your own arm on there. You could put other kinds of sensors. We already have a subcontractor doing a test of a very high performance set of cameras that can go on there. But people can think up other things to go on there as well. And then we have an API so that you can program the platform through the API to do your application. I have a couple of examples of programming it through the API. We have our own application team to kind of get the ball rolling before we have others doing it. And here's a case where they've programmed a map collection and map navigation system that runs on that white box that you see on its back. It actually interacts. A lot of the vision is done on board, but the high-level task of telling the robot where on the map to go is done in the outside as essentially the app for this. And here it is navigating through our lab. We drove it through the lab and collected the data for the map, and here it's using that data to go where we told it to, and it can just go around and around in this space ad nauseum. That insert is showing the obstacle detection, so you can see the kind of visual data that it gets from the cameras. There's no LiDAR on this implementation, so it does both the navigation and the obstacle avoidance using a set of stereo cameras. There's a set on all four sides. It goes downstairs funny because the leg geometry makes it so it's a little bit more reliable if you go backwards than forwards. But naturally, it can figure that out, and the robot doesn't care, especially since it has sensors on all four sides. So this is a slowed version of the thing that's on YouTube. You can watch this to your heart's content on YouTube. And here's another application, which is more of a manipulation application, where we have an external computer telling these two robots to sort of do a three-can Monty. And it's using a sensor in the hand to do the final grasp of the robot so it can see them. And here we've expanded it so there's 4 robots doing the same kind of task, all programmed externally to the basic functionality of the robot, but using all the capability of mobility, controlling the hand, and things like that. So we have a SpotMini here, and Marty Walsh is here. Now, this Marty Walsh isn't the mayor of Boston. This is another one. But he's operating the robot from the corner there. So here the robot's walking with a trotting gait, and it has a bunch of different gaits. There's a walking gait where it moves one leg at a time. Obviously, it's balancing itself. It's got an onboard gyro that's used to sense the orientation of the body. This is a trotting gait. All the coordination is done using that sequential composition. Here the robot's jogging, so it's has a little bit of a flight phase as it goes. The robot's omnidirectional, which means that it can go fore and aft. Here, Marty will show that. And it can go sideways. I mean, this is what you'd expect from a legged system, and it can turn in place. And I'll just do a little show and tell, and then we'll show you the arm. So the robot has cameras. There's one set here. Why don't you rotate around, then you can see. There's actually two in the front, even though we say it's on all four sides. There's two sets. Go ahead around. And there's one in the back, right here. There's a battery that just drops out of the bottom with a quick release. Battery's good for about 90 minutes, depending upon how you're using it. And as I said before, this is a platform. So this is a box that has a special radio in it that, you all have your cell phones, and you would be jamming the Wi-Fi comms with the robot. So when we do a show like this, we use a more sophisticated radio that's in that box. And of course, the arm. This isn't a third-party arm, but eventually we hope that there's a third-party arm on there. So here, Marty's driving the hand around. He's got a little Xbox controller there. And the robot is kind of coordinating all the motions of the body so that the hand can be what you're thinking about. And that's, I think, how biological manipulation works. You think about what your hand's doing, not about what your shoulder's doing. And we're trying to get that in the robot as well. You want to do the stabilization, the chicken head? I love showing off the chicken head thing. So here, the body is being posed and the hand is staying relatively still, which is part of the tools for mobile manipulation. And then you want to do the show-off gaits, the hopping. So the robot's a little bit of a show-off, and it likes to show you that it's really got a lot of chops that it hasn't shown yet. Oh, I almost forgot the other stuff. OK. SpotMini, I'm feeling a little thirsty. Could you get me a soda? So Marty's driving it now, and he's trying to get it to be a close distance to the can. And then there's a sensor in the can, in the hand. This is a hand, not a head. That's used to localize the cup as it gets close, and then it grasps it, and then he brings it and gives it to me. I'm like, oh, thank you. There's nothing in here, but. And then let's do the terrain. We brought some terrain with us, and you're going to put the vision system on. And so now it's using its vision to plan its footsteps. You can see it stepped up onto the box and placed its feet up there. It can see backwards, so it can do it going backwards as well. So in this mode, it's not trying to avoid the box. I don't know if we have it set up to avoid the box, but great. We'll have this after the talk if you guys want to come up, and a few of you can drive. I wish I could give one away as a raffle thing. Maybe next year or the year after or something when we get it to be less expensive. Thank you, Marty, and thank you, SpotMini. So I'm just going to say a couple of words about Atlas, our humanoid robot, which is a longer range program. The robot's very expensive and it's complicated and everything's a little bit on the more fragile side. But it's really connected to our roots in being excited about dynamic control of complex systems. I wanted to make a point that I think a lot of people think that this is the model of a robot system. There's a computer, there's a robot, they talk to each other, control signals go one way, and sensor signals go the other way, and that software makes it all work. But I think that's only half the picture. The fact that the robot is interacting with the physical world is a very significant part of the story, especially for dynamic robots. And that means that if you look in the lower right there, that there are the physics is giving commands to the robot in addition to the computer, and you really need a reconciliation of all that stuff. You have to have some concept of gravity and friction and compliance, either compliance that's built in purpose in the robot, or parasitic compliances, because nothing is absolutely rigid and stiff, at least not if it weighs the right amount. And kinetic energy and potential energy are all things that I think you have to have in mind if you're designing a system that has the right, that's going to have advanced behavior. So we like to think of the software and the hardware design at the same time. So on the hardware side, we've been trying to make some more sophisticated designs of robots. And this is a concept picture where on the left is a big dog leg that has hoses and separate fittings, and each of the actuator components is a separate thing, just like you'd find in in a bulldozer or any other hydraulic machine. And in the center there is the concept that's supposed to look like a biology text, where everything is more integrated and layered together. And so we've been trying to achieve that in our designs. And the first step was to make an upper leg for this version of Atlas that is a 3D printed using laser sintering, and this is a titanium part, and actually we're starting to make them out of a special alloy of aluminum, where this is a cutaway, but inside the part there's hydraulic passages, there's places for valves, there's no fittings, there's voids which make it lighter. And this allowed us to make a robot that's much more compact and lightweight than doing it by having all separate components. Here's some more examples of pieces in the latest version of the Atlas robot that were 3D printed or just engineered to be that kind of design. And the most sophisticated is that thing in the middle, which is only about slightly larger than a football, which is the hydraulic power unit. And it has in it an electric motor, a hydraulic pump, an accumulator, a reservoir, filters, and some other, and a cooling system, all nestled together. And we saved I think we saved we're down to 30% of the weight and much less than 30% of the volume as compared to what we did before. And that let us go from a humanoid. The one on the right is what was used in the DARPA Grand Challenge that we also built, but it was way too big and heavy. We were able to go from 375 pounds down to 190 pounds, and then the current version is about 165 pounds, just slightly less than me, and I find that very irritating that I haven't been able to get to 165, but I'm still working on it. So this is the latest version of Atlas. Actually, this is not the latest. We have one that we're working on now that has a little more strength in some of the joints. But this has all the range of motion and strength that we had in the big robot, but in a much more manageable package. Here, again, we're out in the world testing. This was at a ski lodge in New Hampshire that we took over for a week in order to do testing. This is some mobile manipulation where we're coordinating. Just like with SpotMini, you want to coordinate the hands with body and leg motion. Here we're using the whole body of the system in order to get a lot more mobility to the hands than you would get if you had a manipulator fixed on a rigid base, which is how most robot arms work. Here we're trying to get the robot up to about human speed, so we're testing that. We have this is Ben Stevens, one of the developers, one of the brains behind Atlas. Feeding it boxes at about human rate. I guess he's watching the robot too, but the robot's watching the boxes. Here we have two Atlases doing it. They didn't cooperate as much as we'd like yet, and here we're working on a more dynamic behavior. One of the things about the dynamics of robots like this is that some concepts that are simple for simpler machines really get complicated. So for instance, what's the posture of the robot? That is a complicated concept when you have lots of parts that articulate with respect to each other. Even in the plane, that's complicated. And when you go to 3D, it gets really complicated. And we've been working on some approximate solutions for understanding the posture of the robot. But we also need some more sophisticated things. I love Atlas, and Atlas has been doing some great stuff. I almost called him he. It's not a he or a she. But it is a complicated machine. So one of the things we have been working on for the last couple of years is a thing that has a lot of the characteristics of the humanoid robot, but in a less complicated package. And Handle is that. It still has a leg-like structure, which lets it accommodate variations in the terrain, but it's got wheels that get the best advantage of where there's a flat space. Why not roll on it with higher efficiency? It still has arms, so it can do whole body type tasks where it combines the mobility of the base with the mobility of the arm. And this video has been around a little bit. This is on YouTube, but I'll show it again. And we're working on a version, on a next version. We have it working. What we're going to use it for is a little bit of a secret, but there's a lot of very useful applications that a machine like this can be used for. This is a hybrid system, meaning there's some electrical degrees of freedom and some hydraulic degrees of freedom. Our new one is all electric, although there's no Persian rug problem involved in that application, but there's some reasons why that is easier. So this robot has a fair amount of mobility. I think you'll see it next doing some mobile tasks. Here it's just showing you that it's not a Segway. Each leg is independently suspended. It's got also a balance system. I think, and it can carry some heavy loads. I think one of the interesting things about this robot is it's got some aspects of a lifelike thing because it's moving dynamically and balancing, but it's a form that's not like any biological thing you've ever seen. So I'm going to close. So that's Handle, and you'll hear more about Handle probably next year. So I'm going to close talking about robot emotions. I sat in on a talk before this session where people were talking about robots with emotions and emotional interaction with people, and we don't really do any of that. But our audience, our YouTube audience, has kind of helped do it for us, and they've kind of assigned some emotion to our robots by dubbing over our videos, and I just thought I'd show you too. Here's the guy who...
I love you, Box. Good night, Box. I love you, Box. Good night, Box. Box.
Definitely someone who had their uppers if they take uppers.
Time to make the f***ing donuts. I should get a boot or something. Okay. All right.
Anyway, it's great having people connected, even though sometimes what they make is complicated. Well, we have a big team doing all this work, and thanks to them for their contributions. And as I said at the outset, we're hiring. So thank you. Sure.
So we have time for a couple of questions. So if you have questions for Mark, anybody out there? Yes, down in front.
So when it came to dealing with balance, the traditional approaches have been, working with the center of mass. And what was the big aha moment for Boston Dynamics and having the different approach around it?
Well, so the question is, what's different? Basically, what do we do different than just thinking about center of mass? Or that would be the traditional thing. And let me just back up and say, if you take a chair has 4 legs, or this table, it's balancing. But it's balancing by keeping its center of mass over the polygon that's provided by the feet. It keeps it inside. But as soon as you have something moving, that isn't a good enough calculation, because you have to take the energy that's stored in the motion of the system into account. Or if you have springs like we do in our legs, If you just try and balance statically that way, it's not going to work. So I think the fundamental thing is to say it's a dynamic system. You're going to have to deal with that and not to be afraid of it. And that's where we started, with algorithms that take into account the energetics of the system in addition to the geometry of the feet. Now in our most recent systems using sequential composition, we have a very complicated set of things we do, but they're fundamentally taking into account all those same issues. And the trick is to be able to get through boundaries of the stage space without losing stability. And there's a lot of technique and art to doing that successfully.
Another question? Sure.
Well, I see with the YouTube stuff and you saying you didn't want to call him he type thing. Are you worried about people anthropomorphizing the robots?
I think people should do whatever they want with the robots. Some should anthropomorphize if they want. Others shouldn't. I know the other fella asked me the question about how we felt about the reactions, the emotional reactions to the videos, like people are afraid of them sometimes. I don't know, it's fun seeing all the different ways that people react. Even though there's a lot of blog headlines that say the robots are scary, if you look at our YouTube videos, you see a lot of people like them meaning press the like button. And the ratio of likes to dislike is very high. So that makes me wonder, are people really afraid, or are they, is it afraid like when you go to the horror movie and you're afraid on purpose? Or maybe, and I'm sure there's some people who are truly afraid as well. So, it's interesting. I think our job is to make the robots do more and more, function. And that's what we spend all our time doing.
It's just funny to have a room full of roboticists going, "Aw," when you push over a robot.
Yeah.
Now that you're not connected to Google, will you be doing defense work again?
We haven't decided. The question was, will we be doing defense work in our current state? We haven't decided. Yeah.
The shape of the Spot robot is very antelope-like. And, you were showing the example of handle that's very not drawn from nature so much. I'm curious if there are other shapes and configurations that you consider that sort of meet somewhere in the middle or present other, mobility or dexterity options that we'll see in the future.
Yeah, I don't know about what we'll see in the future, but we've looked at so many different things, both the engineers trying to be practical, artists trying to be interesting. We've looked at all sorts of stuff. This robot, the one we just demoed, is mostly driven by practical constraints on its shape, aside from the design of the skins, which are made to look nice. We were concerned, our first idea for its design was fit in a house, but still be able to reach up onto a counter and down to the floor. That's what made it have longish legs and a long arm. I think having something a little smaller would fit in a house better, but then you wouldn't be able to reach all those places. I think we have to get further down the track of having actual users who are pinging us for the functionality they really need before we do that. Right now, part of the idea of the platform is, as all of you know, there's not this huge customer base yet. Right? We're at that transition from impractical to starting to be practical, and we need to get feedback from use case in order to define some of the details. I think once, though, you have the technology roughly in shape, you can redesign for particular missions as appropriate. Yeah? Great question. The question is, will it ever be able to stand on two legs? We have had it standing on its front legs for seconds at a time. The strength of the shoulders is such that it can't quite step in order to keep itself balanced. And with the feet just planted, it does pretty well, but it doesn't have quite the degrees of freedom to do a handstand, a static handstand. Yeah, we'll pretty soon have it climbing things at least as tall as this table, where each step is as tall as the table in order to be able to get up onto things. Yeah. One of the real embarrassments is how much power is in the computes. This thing has two i7s, which are both quad cores, and we're just throwing away energy. We're working it, but you can't do everything at once. I think there's something like 300 watts in electronics. Now, some of that's not going to go away, but some of it really could, and that's a big fraction of the budget. So there's a lot of progress to be made on what the duration of operation can be. But it's also true that the battery is so easy to remove that we could have it have a station where it changes them out by itself. We've almost done it where someone with a joystick can have one spot take the battery out of another one, but that was just for fun.
One last question before we have to finish up here. There's another question. Right there, you're the last guy.
So you showed some very impressive videos there. The robot was kind of disturbed during attacks. How does the robot detect that this disturbance? How does it recover?
So the tech, there's a lot of sensing aside from the visual system. So when it's grabbing the door handle, it can feel the door handle, and it also has the camera in the hand, so it can see things there. It's got both proprioception in the legs. Proprioception means you can tell what the positions and forces are of the legs, in addition to a gyro. So there's a lot of information that can give you a hint that you're not on track of where you wanted to be, and we use that for it to decide that it can't keep doing the part of the task it's in now, and it's going to have to either backtrack or somehow recover from that. I think that's most of as good an answer as I could give to that.
Okay, so with that, I want to thank you all for coming to the inaugural Robotics Summit and Showcase event. Boston now and the robotics sector writ large has a technical design and development event for people building commercial class robots. That didn't exist before until this event. I want to thank all our sponsors, certainly Harmonic Drive and Sertronics, the Platinum and Diamond sponsor respectively. I want to thank Mass Robotics. We have Joyce Sidopoulos and Tom Ryden back there. Raise your hands, please, for supporting us. I know I've been introducing a lot of people, but there is actually an associate of mine, Steve Crow, if you're out there. There he is right there. The only reason he hasn't been up here is age has its privilege, and I've done this before a couple of times. So, Steve, certainly the WTWH media team, that would be Scott McCafferty. I think he's back there somewhere. Yes, raising his hand. And certainly Jen Kolaski and the team of the support people. Jen's around here somewhere. The other folks for WTWH here are down in the front who helped us out with some of the operational stuff. So thank you then. We are back in Boston next year, June 4th through 6th, down at the World Trade Center. We're doubling the size of this event. I'll have a year with my associates to plan this event. So you're now in the premier robotics cluster in the world, or number one or number two, you can argue about it. And we're going to be running this event here. So I hopefully will see all the rest of you there next year at this. We have all your contact information, so we'll be reaching out to you in terms of the new event, but also to get back to us on what worked and what didn't work with this first event. And we'd be very happy to incorporate your opinions and comments into what we're developing for next year. So with that, I'd like to thank Marc Raibert for finishing up as the last keynote, and thank you all. Thank you very much.
Thanks, Dan.